for those who don't know me, I'm Andrew Foster, and I've been was asked to put together a series on environment and development this year for IBIS, and so we've mostly had economists to date, but I'm very pleased to have a non-economist today, and I guess an atmospheric environmentalist, but she has lots of different credentials, it looked like to me. I think one of the most important credentials, however, she's a Brown undergraduate, and so we're really delighted to welcome her back to the Yale School. All right.
Thanks. Well, it's fun to be here. I think I've been back twice in 25 years, so I'm really impressed with how things have changed. It's really fun to see, and it's great that there's so much environmental activity going on here now. I'm going to talk about opportunities for co-benefits in mitigating air pollution and addressing greenhouse gas emissions, reducing greenhouse gas emissions in China. And this work has been done collectively by me and members of my group who I've highlighted here, and you'll see them throughout the presentation. So air pollution in China is extremely serious. The visibility is frequently, like you see in some of these pictures, children get checked into hospitals when air pollution episodes are particularly bad and breathe filtered air. Air pollution affects health around the world. You can see here premature mortalities due to air pollution are among the highest in the world in China and in northern India. There's also elevated levels in Europe and in the United States. What you see here are data from the US Embassy in Beijing. This was one of, I think, considered a diplomatic breakthrough on the part of the United States, where the State Department decided to set up monitors for fine particulate matter at the US Embassy and various consulates around China. The first one was in Beijing, and what you can see here is PM2.5 concentrations starting in July of 2008, and I have here up through the end of 2015. What you can notice, however, is that in blue are the Beijing 24-hour average concentrations, and in red is the US PM2.5 standard of 35 micrograms per cubic meter, and the World Health Organization standard is down here at 25 micrograms per cubic meter. So air quality in Beijing rarely gets as low as the World Health Organization or US standards. In the US, as you look out the window here, due to our very good air quality regulations and emission controls, we rarely exceed these standards. Here you can see concentrations in multiple factors higher than the standards. There's a slight trend downwards, which the Chinese are excited about, and you can see a seasonal variability in concentrations, with the highest levels typically occurring in the winter. And that's due to the use of coal for heating and cooking, as well as changes in meteorology. So here I am at Tsinghua University in November with 3 Tsinghua professors who insisted we all put on face masks before we left for dinner. So this is something that is ubiquitous and really affects people's daily lives. In addition to having severe air pollution, however, China is also the largest emitter of carbon dioxide in the world. In 2006, it surpassed the emissions of the United States. You can see it's now about twice the level of the US, about 3 times the level of the European Union, and India is now rapidly increasing as well. What's interesting, however, is that you can see that the emissions from China appear to have stabilized recently, and one question is whether or not they're going to peak and continue to rise, or if they're actually already on a bit of a downturn. In 2014, 15, and 16, the global emissions remained about constant, which is actually some very good news for climate. But the future is uncertain, as the future always is. In terms of per capita carbon dioxide emissions, the US still leads the world. Here you can see that our per capita emissions have begun to come down, which means that as our economy has grown, our energy intensity has decreased. China's CO2 emissions per capita have risen dramatically starting around the turn of the century and have surpassed the world average in about 2005 and surpassed the European Union in about 2012. And so they're no longer really an unindustrial developing country. They're a country that has large differences in per capita emissions. And they're really sort of right there in the middle of the global per capita emissions. Of course, climate change is real and it's happening. Here you're looking at 2015 temperatures around the world compared with the average at each location for 1950 through 1980. And so you can see that the temperature increase in many parts of the northern hemisphere is about 3.5 degrees Fahrenheit. It changed over that time period. And so we have a real problem. We have a developing country that has high pollution levels and is a high emitter, and it needs to clean up its air in order to protect public health, and it also needs to peak and begin to reduce its CO2 emissions. And so one of the things that we try and think about is how can it do both of those things simultaneously? Because interventions can sometimes just improve air quality, like putting a scrubber on a coal-fired power plant, removes the particles that are being emitted, the SO2 that's being emitted that turns into particles, but it costs you energy to operate. And in addition, as you remove that sulfur, as I'll tell you in a minute, you're actually reducing in the atmosphere a reflective aerosol, which then reveals the long-term warning of the greenhouse gases. So let's just take a look at that for a moment. This is a key figure from the Intergovernmental Panel on Climate Change. For those of you who work on this type of thing, this is very familiar. For those of you who don't, it's a little bit intimidating. So let me walk you through it briefly. So what this figure is showing you is the radiative forcing by emissions of individual gases and aerosols. And what radiative forcing basically means is the amount of heat that's trapped in the atmosphere by the change in the concentration of a gas or particle in the atmosphere relative to pre-industrial time. So if you put carbon dioxide into the atmosphere, it stays in the atmosphere for a period of time, and the difference between CO2 today and CO2 in the pre-industrial period results in a certain amount of trapping of heat. And that's the radiative forcing for CO2 here. CO2 has a long lifetime, and so here you have a radiative forcing of about 1.7 watts per square meter. So the amount of heat that's being trapped in the atmosphere per square meter by the carbon dioxide that's now in the atmosphere compared to the pre-industrial period, it's about 1.7 watts per square meter. And these other long-lived greenhouse gases also have positive radiative forcing, meaning they also trap energy in the atmosphere and warm the planet. If you go down here, you notice that these aerosols have a negative radiative forcing. That means they cool the climate. And they do that because they're reflective, they're light-colored aerosols in the atmosphere, and just like a white umbrella, they reflect incoming solar radiation back to space. And so if you see here, you can see mineral dust in blue, but you can see sulfate in this yellowish-green color. Sulfate is emitted a lot from coal-fired power plants. It's SO2. SO2 contributes to the formation of fine particles, which is bad for health. It contributes to the formation of acid rain, which is bad for ecosystems. But it's also a light-colored aerosol, so it contributes to cooling of the atmosphere. So as you reduce your sulfur emissions by scrubbing your coal or running these desulfurization processes, you improve air quality, you protect human health, and you reveal the long-lived greenhouse gases' positive radiative forcing. Because it's a little bit like having an umbrella that's reflecting incoming solar radiation back to space, and you close your umbrella. You get rid of that SO2. Or you get rid of that nitrate here, or you get rid of the organic carbon. And you lose that cooling ability from those aerosols. In addition, those hydrophilic aerosols, those particles that attract water, act as cloud condensation nuclei. And so they whiten clouds, because the more small droplets you have in a cloud, the whiter the cloud becomes. And if you get rid of those aerosols, you lose this negative radiative forcing you get from whitening your clouds. And the challenge you face here is that these aerosols have lifetimes that are very short, on the order of days to weeks, whereas these greenhouse gases have lifetimes on the order of decades to centuries. So as we clean up the air, we lose this negative radiative forcing really fast. But we still keep the positive radiative forcing from these long-lived greenhouse gases in the atmosphere. And so that's an additional challenge and complexity that's being faced, because what this means is as we clean up our air, which we need to do to protect health and we need to do to protect ecosystems, we have to be even more aggressive at reducing the emissions of these long-lived greenhouse gases that are going to stick around for a really, really long time. And adding to this fact is that the climate right now is not yet at full equilibrium with the greenhouse gases that have already been emitted. And so one thing I often ask people to think about is, if you're cold at night and you get into bed and put on a big blanket, do you warm up immediately? No, you don't warm up immediately. It takes a while for the blanket to trap enough heat that you warm up, that the air close to your body warms up. So likewise, right now, the Earth is not yet in thermal equilibrium with the greenhouse gases that have already been emitted. So even if we stopped emitting them tomorrow, the Earth would continue to warm for some time. Just like if you get into bed and you're cold, you put on your blanket, you're not instantly in thermal equilibrium. It takes a while for the blanket to trap heat that warms you up enough that you feel comfortable. And so we really have a big challenge because the Earth is warming. People want to clean up the air. How do we do it in a way that maximizes benefits for both? And that's what my group is trying to think about and look at. Feel free to interrupt if you have questions.
Okay.
Yes. What's your question?
How big is, I mean, let's pretend we got half the sulfur out of the air. You know, I'm looking at the yellow block there. How big of a deal is that? Like,
So I actually have an answer to your question in a slightly different form in this slide here. So this is a paper that was done by a postdoc who was in my group for a number of years, who's now at Columbia. And what we did here was we did simulations using the Geophysical Fluid Dynamics Lab's coupled chemistry climate model. And we took what's in the Intergovernmental Panel on Climate Change's representative concentration pathways for greenhouse gases. They have different pathways of the changing concentrations depending on the radiative forcing. So this is the one with the least concentration increase, and at 2100 it's supposed to be at 2.6 watts per square meter is the green one, and the red one is at 8.5. And so here, 8.5 watts per square meter in 2100. And so the solid lines are the RCP, which you'll have to just believe me because I don't have a figure showing this right here, that the expectation is that around the world people will care enough about air pollution that they're going to reduce the emissions of air pollution. And all of these RCPs show aerosols coming down by 2050, very substantially, by 50% or more everywhere, around the world on average. So if you have that happen, you look at the red lines. That's the projected temperature increase that would result from having the aerosols drop down and having the greenhouse gases go up. But then what we did was we looked with the dashed lines at what happens if you kept those aerosols constant at 2005 levels. Instead of having them come down like they're expected to do by about 50%, what would be the difference in the temperature in 2100 of keeping the aerosols at levels they're at right now, or basically dropping them by about 50%. And you can see that there's an additional about 1 degree of warming in all of these scenarios that results just from removing the air pollution, just from removing the aerosols from the atmosphere. You get an additional 1 degree of warming beyond what has already been projected due to the long-lived greenhouse gases. Does that address your question?
It sure does.
Okay, good.
It adds up to 3 degrees, essentially.
So it's the delta, in each of these scenarios, it's the delta between the between the solid line and the dashed line.
Right.
One
That-
extra degree.
One extra degree.
1 to 2 degrees. It's pretty constant, actually, and the reason it's pretty constant between all these different scenarios is that all the RCPs have about a 50% decrease in aerosol loadings in the atmosphere.
The way they're configured in the IPCC report.
Correct.
Okay.
Yes. So we did that, but then we also went on, and there's been a lot of concern about climate change is going to affect the concentrations of aerosol in the atmosphere. And we were curious about how much aerosols decreasing, as they're projected to do, affect radiative forcing versus how much the increase in aerosol concentrations that result from changing climate do. And this graph is basically showing you that if you look at the dashed lines, this is if we don't change the emissions of aerosols at all. We keep the emissions the same as they are in 2000, and we run forward the climate model to 2100, allowing the climate to change based on the greenhouse gas concentrations. And what you can see here is that aerosols increase a little bit because of climate change. The aerosols go up a little bit. But it's much, much less than they would go down in terms of what the RCPs are projecting alone. So reducing our emissions improves air quality more than climate will harm it, is basically the conclusion from this. Okay? Okay, so I'm going to focus now more on China, rather this initial discussion was global. And China's goal right now is to simultaneously address air pollution and greenhouse gas mitigation. Air pollution is a local issue. It's estimated that about 1.6 million premature mortalities occurred in China in 2013 due to air pollution alone. And recently China's declared a war on air pollution, and their goal is to reduce PM 2.5, which is fine particles 2.5 micrometers in diameter or smaller that can get deep into your lungs, by up to 25% relative to 2012 by this year. And they're very serious about that. They're working hard to do it. And in addition, as you saw, they're the world's top carbon emitter, and their Paris Agreement was to peak their CO2 emissions by 2030 or sooner. And an open question is where the peak will occur. Is it going to occur here? Is it going to occur here? Is it going to occur here? And then after that, hopefully come down. So the key question that we want to address is how can these goals be achieved with maximum co-benefits? Oops, I'm sorry. And so there's two opportunities really to achieve both. One is to increase efficiency of any process you're doing that uses fuel. Increase the efficiency, and you can reduce your emissions of greenhouse gases. You can reduce your emissions of air pollutants. And another is to electrify the economy. And electrify the economy ideally with as much non-fossil fuels as possible. And electrification helps because electrification is like a centralized source of power, in the case of a coal-fired power plant, which China uses for more than 65% of their electricity right now. And you can put controls on those emissions easily, right there, and you can monitor them easily. And it's very difficult to put controls on individual coal stoves or individual vehicles. And then in addition, if you use renewable energy in the electrification process, you can reduce both your emissions of greenhouse gases and air pollutants. So that's an opportunity in that center area to do both. So this is just a brief schematic of sort of how we do this type of analysis. So we start by taking current emissions. We collaborate with people at Tsinghua University in China and get current emissions from their emission inventories across China. And then we look at particular interventions and say, okay, how much would your emissions of air pollutants or greenhouse gases change due to this intervention? And then we use the sort of state of the science air quality model called WRF-Chem, which is a regional air pollution chemistry transport model, to calculate what do those emission changes mean for a change in air pollution. And then we look at what does the change in air pollution mean for health, and what does the change in greenhouse gases mean for climate. And so I'm going to give you a schematic here. And so I actually was just at the World Economic Forum in Davos, and I had to give a talk in 5 minutes to summarize everything I did. So I came up with these figures. And so I thought I'd put them in at the very beginning, because it gives you sort of a schematic of the answers, the final answers we've come to, and then I'll go into some more details later on. So what you see here is that work we did looking at how much does increasing efficiency and end-of-pipe controls how much does it result in improving air quality, and how does that change premature mortalities, and how does that change CO2 emissions? And so increasing efficiency and end-of-pipe controls reduce both premature mortalities by improving air quality and reduce CO2 emissions because of the improvements in efficiency a bit. Not a lot. I intentionally left the y-axis blank in terms of numerical values. It's a little bit more complicated than the schematic shows. And then if you electrify with coal, you get a larger reduction in premature mortalities because, like I mentioned before, you're controlling your emissions in a centralized source where you can monitor and enforce it more easily. But it doesn't reduce CO2 emissions that much because you're still burning coal, which is a very carbon-intensive fuel. But if you electrify with coal and you add as many renewables as possible to it, you get a larger reduction in premature mortalities and a very large reduction in CO2 emissions, depending on how much renewables you're able to incorporate. And so one of the challenges of incorporating renewable energy is that it's variable. The sun doesn't shine at night, the wind doesn't blow all the time. And so we have challenges of figuring out how do you actually entrain that into your electricity supply. And we've started looking at that, and China has been building long-distance transmission lines that can bring power from the western part of China to the eastern part of China in order to utilize electricity without incurring some of the air quality penalties in the eastern part of the country. They've been increasing their renewable power capacity dramatically recently. They currently have the largest wind power capacity in the world. You can see here this exponential growth, 2010, 2015, and projected for 2020 for wind. And you can see cumulative installed solar PV capacity in China also increasing dramatically. Here's projected for 2020 and goals for 2030. And in Davos, Xi Jinping gave a really remarkable talk, I thought, indicating a major commitment that the Chinese have to increasing renewable energy and to sharing it globally. If the US pulls back on renewables and pulls back on international trade, China is planning to move in. So let me just walk you through this methodology in a little bit more detail than I showed you a few minutes ago. What we do is we start with a baseline emission inventory, then we model changes in emissions of reactive pollutants and greenhouse gases. Then we model resulting changes in the concentrations of air pollutants. We model changes in human exposure, model changes in mortality, and model changes in mortality that result. And we use regional atmospheric chemistry transport models, which for those of you who aren't familiar with this type of thing, are basically models which try and capture everything that happens in terms of air pollution in the atmosphere. So we include emissions from the surface, like I mentioned, and we include chemical transformation of the pollutants in the box. We include transport into the box, this chemical transformation, transport out of the box, and the solar radiation which drives all of this chemistry in the box. And these boxes then get stacked on top of each other so that we can include transport vertically as well as horizontally. So we can see where does the pollution come from, where does it go to, and then what are the impacts that it has. And so what you're seeing here is a simulation using WRF-Chem, and we're showing here fine particles, PM2.5. And so you can see the concentrations here, January, April, July, and October, and the annual average. And what you can see here, this dot is Beijing. You can see a really large enhancement in winter in the Beijing-Tianjin-Hebei region, which is the North China Plain. What you're seeing here is a comparison of the model simulations for January, April, July, and October compared with the US State Department measurements you saw earlier. And the agreement is reasonably good. Not perfect, but it gives us some confidence that what we're doing is okay. And then what we are going to do is, I've said already, is to then look at interventions and how they change the concentrations. So this is a paper where we looked at the effect of these small coal stoves on ambient PM2.5 concentrations. It's something that's actually been overlooked quite substantially in efforts to clean up the air. There's been a lot of attention put on the power sector and on the transport sector because of their emissions. But as you can see here, these stoves are extremely dirty. They emit a lot of fine particles. They have no chimney, so they first get emitted indoors, or they're used outdoors, outside of people's homes. And they burn these coal briquettes, or they potentially burn literally just chunks of coal that people can dig up, in their neighborhoods or not too far from home. And the contribution from them to PM2.5 is enormous. So this is an emission inventory developed at Tsinghua University, looking at the different constituents, the different pollution constituents here, PM2.5, fine particles, black carbon, organic carbon, sulfur dioxide, nitrogen oxide, in Beijing, Tianjin, and Hebei, the annual average, and then for January and February. And in orange are the residential sector emissions and their contribution to each of these. So in winter, if you look at PM2.5, you can see that it's responsible for over half the PM2.5 in the North China Plain. These other sectors, industry is important, but the power sector has been cleaned up a lot. The coal-fired power plants that China is using now are cleaner than most of those in the United States. And then the transport sector, according to emission inventories, is a relatively small contributor, though there's thoughts that the emission inventories may be underestimating emissions from the transport sector because enforcement is so poor relative to
The stoves are mostly heating or heating and cooking?
they're heating and cooking.
Okay.
They're heating and cooking. And they're used in sort of suburban, rural areas. But these, I mean, you don't think of Beijing as being at all sort of suburban, rural area, but the provinces right next to it are more so. And you can see even in Beijing in winter, those stoves are really an important contributing factor for their PM2.5 emissions.
Is that presumably then for heating at that point? Because those areas would be electrified for cooking, no? Or is that not correct?
Every home in China, for the most part, has an electrical connection. So if they're using these stoves, it could be for both cooking and heating.
Even in the sort of urban areas? I would just think in urban areas it would be more likely they were just used for heating, but that's not right.
So I think if they're used, I'm not sure exactly, to be
I
honest,
see.
but into apartment buildings, you're probably not using that kind of stove. But in the more agricultural regions, it could be that they're using those stoves for both cooking and heating.
Do you know if there's been much transition to use of piped gas in the cities?
So that's actually later on we're looking at gas use, but so in China, north of the Hangpu River, they use district heating. And they basically have cogen plants where they pipe hot water around the city or steam around the city and use that for heating. It's on a very strict schedule. I was in Beijing in early November. The heating season hadn't started yet. It was about 40 degrees outside, and there was no heat in the Peking University hotel. And so I said, I'm freezing, can I have a heater, electric heater? No heater. Can I have an extra blanket? No blanket. So I wore my coat and my hat, and I mean, I survived the first night. Then a sort of illustrious professor said, she needs a heater, so I got in my electric heater. But it's on a very strict schedule, and I actually see, while I was there, we were wearing face masks. I think you came in after that photo, but I think what happens is when it gets cold and the district heating hasn't been turned on yet, people start using electric heaters and these coal stoves just to stay warm. And so it increases the air pollution. But we've looked at the possibility of moving to natural gas. And the piping for natural gas is very limited. China doesn't have very much conventional natural gas right now. But what we find is that, exactly as you're hinting, basically getting rid of these stoves and using natural gas or using electricity or using LPG, which is a standard substitution.
So you're saying both piping steam and hot water, but also piped gas to replace the coal stove is a possibility?
Yes. Yes. So here, what you can see is the benefits for PM2.5 of eliminating emissions from these stoves. So this is using the regional atmospheric chemistry transport model. So if you look here at Beijing, let me just walk you through this, sorry. So we did a base case where we looked at the air quality resulting from the standard emissions. And then we looked at removing residential emissions from Beijing. That's BJR in blue. And then we looked at removing residential emissions from Beijing, Tianjin, and Hebei. And that's in red. And so what you can see is that in Beijing, this is base PM2.5 emissions. When the base PM2.5 emissions get to be large, your reduction in PM2.5 that comes from removing these residential stoves is quite substantial. It can be as much as 50% of the PM2.5 in the ambient air. And in places that are like Tianjin, what you see is that I'm sorry, so let me just finish on this Beijing slide, figure. If you remove those emissions just from Beijing, you get a small improvement. But if you remove the emissions from Beijing, Tianjin, and Hebei, the emission reduction has a bigger effect on Beijing air quality because the air moves through the region, there's regional transport, and reductions in the surrounding region have benefits within Beijing. And here for Tianjin, you see, because Beijing has lower emissions, a small improvement with reductions in Beijing, but a huge improvement if you reduce emissions from Beijing, Tianjin, and Hebei as well. And so here for Tianjin, you can see that if you remove the emissions from Beijing, Tianjin, and Hebei, you get about on average a 43% reduction in PM2.5 in January and February. So really substantial improvement, but with the key finding that regional transport of air pollution is very important. And so the Chinese government has typically in the past said we're going to take industry and move it from the center of the city out. And that has a limited benefit because the pollution then will be transported back in as well. So a regional way to address your air pollution problems is very important. Okay, so that paper stopped with just the ambient air pollution impacts, but we do go on in other work to look at the human health impacts. And so I'm showing you here a paper that came out a few years ago in which they went beyond the standard epidemiological analysis which has been done in the United States, where what was done was what were called cohort studies, where you follow a population over a number of years or decades. And in the case of the 6-city study in the United States, they followed populations where as similar as possible in 6 cities that had different levels of air pollution. And what they found was a curve that looked basically like this, that as the concentrations of fine particles increased, the relative risk of a premature death increased linearly. But what was realized was that in highly polluted places or among smokers who are exposed to extremely high levels of air pollution, everyone isn't dead. If you had actually had a relative risk curve that you extrapolated straight up to these concentrations, you would be reaching a 90% mortality rate. And that wasn't what was seen. So they realized that as you get to higher pollution levels, this curve must flatten. And so they used this data from smokers to say it flattens. And the Beijing pollution levels are often sort of in this region here. It's not exactly clear what's going on in this midpoint when there's limited long-term data available. Cohort studies haven't been done in China yet. But the understanding now is that this must flatten. So we take this into account in our studies now where we simulate the air pollution concentrations over a wide area, and we look at the change in air pollution over that area, and we take into account whether, say, a region is super polluted or less polluted. Because if you reduce your pollution levels a bit when you're at this high part of the curve, you don't get that big of an improvement in health. But if you reduce your pollution levels where this curve is steep, a reduction in pollution will lead to a large health benefit. Mm-hmm.
So these graphs, I don't quite understand how they're sort of aggregating sort of short-term exposure and long-term exposure. Is this sort of what you'd expect if you were exposed over sort of the full lifetime, or what are we?
This is long-term exposure. So these are studies that go on for decades, and they track the cohort of people over decades, and they see, given their exposure over that time period on average, what's their relative risk of
average exposure
over a long time period? What's their relative risk of premature mortality?
Could I ask another detail on this? Since you mentioned smokers, do these studies, do they have the ability to distinguish between mortality experiences of smokers and non-smokers? I'm just thinking about how the local environment, that is the residential environment, like the coal stoves, mm-hmm. The smoker's like a coal stove in the home.
Right.
And even if you're not smoking, you're exposed to it. And I'm curious about the relative impact of the smoking in the home and then these particulates in the air outside of the home that are modeled in these kinds of studies you're talking about.
So I don't really know the detailed answer to your question. What I'm showing you here is work that obviously other people have done that we use in our analyses. And so we use this because we look at the ambient air pollution levels, and we use these curves to evaluate the health impacts of the ambient air pollution levels.
So you don't
So-
know how smoking could be taken into account?
Well, smoking is used to determine the curves here, where in the US they do have that data that they're analyzing. But in terms of, is a smoker in China exposed to something different than the person, that we're only looking at the ambient air quality and holding basically everything else constant. Okay, and so then what we do is, this equation looks a little complicated, it's really not. We're trying to evaluate the change in mortality. So the change in mortality is going to be a function of the population that's exposed, the base mortality rate of that population, and then the change in relative risk due to the exposure at this concentration of the scenario we're looking at divided by the concentration of the base case, -1, so you get a percent change basically. And then multiply by a population, so you get a number change. And so in this case, what we're looking at is what is the air quality and health benefit of long distance transmission lines that China is in the process of building right now. What you see here are these long distance transmission lines that are either built or planned to be built that take power from the western part of China to the big demand centers in the east. And the reason they built these was to reduce air pollution in the east. It's part of their war on air pollution. But what they are largely doing is they're building the power plants in coal-rich areas so they can build coal power plants in the west and move the power to the east. But what we also looked at was, what about if these long-distance power lines transmitted renewable energy from the west too? Because this is Inner Mongolia, it's very windy. As you move further west, you get more and more solar radiation. So you could capture renewable energy on your transmission lines. And so we have these 3 cases. We have a base case, and here you're looking at the emissions of SO2 in the base case, and then the reduction in SO2 in what we call coal by rail, where they do what they do right now, bring coal from the west to the east and burn it in the east. But in this case, they're shutting down dirty old coal power plants and putting in cleaner new ones. This is coal by wire, where you're shutting down these dirty ones in the east and building cleaner ones in the west. So you get a big reduction in the east, but you get an increase in the west. And this is the change you get if you do renewable energy plus coal. So you get a much smaller increase in the west and a larger decrease in the east. As here you see the wind resource potential. You can see it's very windy up here in Inner Mongolia. And you can see solar radiation potential, which is largest outside of this cloudy, polluted part of eastern China. We've actually done some work, which I don't have time to talk about today, looking at how much attenuation of solar radiation occurs because of this air pollution. And it's quite substantial. So this is a summary here of what I just told you about these different scenarios. And now what I'm going to show you are a series of figures where I'm going to try and squash all these results together into a sort of consistent format so we can analyze the reductions in CO2 from a particular scenario and the reductions in national total premature mortalities that result from those scenarios. And so here you see coal by rail, this dot, and coal by wire here, where you get a small decrease in CO2 emissions because you're shutting down inefficient power plants and building more efficient ones, and a small decrease in premature mortalities because you're cleaning up the emissions, reducing the emissions. But then we call this transmission hybrid. If you can add renewable energy to that mix, you get a much bigger decrease in CO2 emissions. So just using these 12 transmission lines, you can get nearly a 4% reduction in your CO2 emissions if those transmission lines were to be powered with 60% renewable energy coming from the west. We also then looked at what about improving energy efficiency in the industrial sector, replacing inefficient old power plants with more efficient clean ones, replacing high-emitting vehicles with average fuel vehicle emissions, replacing 20% of coal-based stoves with liquid petroleum gas, or combining all of them. And you can see that you can get a decrease in CO2 emissions in all of these cases with the industrial improvements in energy efficiency being the largest of what we looked at. And these scenarios were all chosen to be stuff that's immediately feasible, where there's policies already in place that would allow this to happen, sort of what we call counterfactual cases. And if you did all of this, you could get a 10% reduction in national total premature mortalities and about a 5% reduction in CO2 emissions. Technology currently available, policies which could be implemented easily to achieve this in China today. So,
Could I ask another question?
yeah, absolutely.
So if in Inner Mongolia you build some new coal plants, you transport the power through
Mhm.
power lines, the new coal plants are going to be polluting, but there's not many people there getting the impact of that pollution.
But it's on the steeper part of the curve because it's cleaner, so each increment of pollution
Yeah, no,
will have a
it's
bigger
cleaner.
effect.
I agree that it's cleaner, but
Mhm.
there's also people there who are newly exposed
Correct.
to something they weren't getting, but there aren't, because there's a very low population density.
That's right. And so that's
So
what
that's
what you see
a
here.
plus.
That's right.
That's a plus.
Hmm.
But then
That's
I
coal
just
power.
wonder to what extent the pollution also moves.
Yes, we account for all of that. And I don't have the figures that show that, but we do all of that because in the
How far does it? I want within the Beijing area. I'm sure it moves around a lot, but across these large regions, does it also move? Like, for example,
Yes,
if
so-
we
so-
put it all in Montana, would it all come back to us anyway? That's the kind of question I have in mind.
So we've done other work, which I won't talk about today, looking at intercontinental transport of air pollution. And if you go to my website, for those who are interested, you can look at animations of transport of pollution from Asia to the United States. And lots of work has been done looking at transport from Asia to the US to Europe. It takes about 2 weeks to move from China across the Pacific to the United States. It takes about a month to move around the northern hemisphere at around 30 degrees, 35 degrees latitude. But it gets diluted as it goes, and so the people who get the most benefit from emission reductions are those who live nearby. But there is dilution, but it does go a long way. And so different pollutants will come out of the atmosphere at different rates. For example, SO2 is soluble, so if it rains, it'll come out. If it's not, it'll stay in the atmosphere for a long time. Yes?
What's the assumption about energy transmission efficiency and how much additional energy you need if the plants are further away?
So we just, I can't remember exactly. I think we have a certain loss rate for a certain distance of the transmission lines, but I don't remember exactly what that is. Okay, so in the interest of time, so this is basically showing what you just saw, sort of in a bar plot form. I think that the message is the same, that in terms of air pollution related deaths, you get similar benefits, but in terms of carbon emissions, improving your energy efficiency in the industry sector is extremely valuable. And then different strategies lead to different regional distributions of health benefits. And so you can see the improvements in energy efficiency for the industrial sector result in improvements in industrial regions. Cleaning up residential stoves benefits this North China Plain area the most. And so, as you point out, different interventions lead to different benefits in different places. Different people will benefit depending on what is done. So a second thing, another thing that we looked at was China's planned synthetic natural gas production. So synthetic natural gas basically means gasifying coal. And whenever you do an energy transformation, it costs you energy to do that. So if you gasify coal, you have additional CO2 emissions which result. But when you gasify coal, you can remove all the air pollutants. And so you can burn a clean fuel, which has big benefits for health. So this is one of the examples where you have disbenefits for climate by trying to address your air pollution. And you can see here there are plans for synthetic natural gas. And so we took the 2020 scenario target of 57 billion cubic meters of gas, and we look at where can you deploy that gas. If you're going to actually make this stuff, where can you deploy it, which would have the biggest benefits for air quality and health and the smallest penalties for climate, for greenhouse gas emissions. And so what we found, and again, this is squishing a lot all together, is that if you put the S&G into the residential sector, which is here with a circle, you get the largest reduction in premature deaths and the smallest penalty in increased CO2 emissions. And here you can see the power and industrial sector. You get a larger increase in CO2 emissions and a smaller benefit for health. And why do you suppose that could be? Why would this be? What's that?
Where the factories are, is what you're talking about, the industrial one? or-
Elevation.
Ah.
The inefficiency of the stove.
Yes, that's right. The inefficiency of the stoves. So stoves are super inefficient and super dirty. So they emit a lot of particles which are really bad for health. And so if you put the synthetic natural gas into that sector, you can get rid of a lot of that particle and improve health. And because they're so inefficient, you don't get a huge penalty for CO2 emissions. In these other sectors, they're fairly efficient combustion processes already, so you don't get that big a benefit for for health because there's controls on it already, and you do get a big disbenefit for CO2 emissions because they're burning relatively efficiently already. However, natural gas has a lot of benefits and attractions because it's clean. It's a clean fuel. So we then looked at, instead of synthetic natural gas, what if you used conventional natural gas? China happens to have very little conventional natural gas available domestically, but they now have agreements with Russia for gas pipelines. And they're also pushing super hard on developing their shale gas, their unconventional gas, like we have here. And so if they were to burn natural gas, you get a clear decrease in CO2 emissions in all of these cases. The same health benefits, but a decrease across the board for CO2 emissions. Especially assuming that the leakage rates of methane are not too large. Yeah?
So one question I have about these graphs is about the cost of these various things. It strikes me that the policymaker who wants to get reelected in China or reappointed or whatever.
You don't have to worry about that.
Yeah. is going to be worrying. Is going to be thinking about, okay, it matters a lot that we reduce air pollution, and it matters a lot that that's cheap, and getting co-benefits with climate change is a nice thing on the margins where possible. But that's going to be lower on my priority.
So you sound like you're coming from a capitalistic economy where cost is of paramount interest. In China, it is a factor, but it's not nearly as important a factor as you would expect from experience in the United States. And so, for example, they build these mega projects in order to solve a problem. They're moving the Yangtze River water north, building huge, channels. They built those power lines. According to our calculations, economically, this doesn't make sense. They're building them. I mean, they're half built already. The plans are to continue building them because they want to address air pollution. What we find is that unless they incorporate renewable power on those power lines, simply replacing the power plants where they exist now with cleaner, more efficient ones would do almost as good a job. We didn't do all the cost calculations, but I don't think they did either. And if they did, they didn't change their decision to build those things as a result of it. There is some factors. So for example, in replacing the residential stoves, coal is dirt cheap, literally. And so if they're going to replace it with LPG or electricity, there are discussions if we need to subsidize the fuel for the poor to be able to afford to buy it. We need to be able to subsidize the stoves. And that's very expensive to do, for everyone. But subsidizing it on the margins in order to improve air quality might economically actually be a super good idea because relative to your alternatives of, transforming something else on the margin, it might be better. I'd love to work with economists. We haven't done these economic calculations. I mean, if anyone here is interested, I'd like to talk to you because...
Another factor is that they are looking for ways to spend a lot of money on something that's worthwhile as a way to stave off the world recession over the last decade. And they've done it very successfully. And so on the one hand, you might say this particular policy doesn't make economic sense. But on a macro level, the amount of money that they're spending on high-speed rail and on all this kind of stuff brought together has had, so far, until they go too far into debt, a positive impact. on the
So I
economy.
agree with that. I think that's an important point because, I mean, they have an industrial policy that, for example, they want to develop electric vehicle technology in order to share it with the world and sell it. They want to develop this renewable technology in order to sell it to the world. And so there's a leveraging that's going on. They might invest things now that don't make sense economically in the short term, but in the long term, they're developing a technology which will then bring benefits down the road. So let me just talk briefly, and then I think I'm getting close to the conclusions on looking at the future. So what I showed you up until now are things that could have been done already if they had chosen to do them. And now I want to just look quickly at solar PV, their 2030 goal of 400 gigawatts, industrial energy efficiency improvements, replacing residential fuel use, and then specifically, especially at electrification. And so here, I've changed scales, so everything up until now was up, with the national CO2 emission reduction was only 6%, that whole x-axis. And so this increased penetration of PV electricity, their goal for 2030 of 400 gigawatts, is as good as anything else we've seen so far in terms of CO2 emission reductions, and it's comparable to on the premature deaths. In terms of energy efficiency for the industrial sector, you can see that it is beneficial for CO2 and for national premature death reduction. But the important thing really in our findings is the role of electricity and the role of increased penetration of non-fossil electricity. And so if you look here, this is what happens if they electrify with coal, with a moderate penetration rate of coal. So that means electrifying 30% of their vehicles and residential stoves, mainly with coal power. Coal power is now about 70% of their electricity generation. And the ambitious scenario is electrifying half their vehicles and residential stoves, mainly with coal power. And you might say, electrifying half their stoves, this is really crazy. How in the world are they going to do this? But when I was in Beijing in November, I met with someone from the NDRC who runs the Energy Research Institute's modeling efforts. And he says, this is part of China's new industrial policy. We're going to design and build electric vehicles. We feel we can compete globally more effectively on that than we can on hybrid vehicles or diesel vehicles. And right now they have a plan in Beijing where they've sold, I think for 2016, 60,000 electric vehicles, 90,000 internal combustion vehicles, because they put a cap on the total number of vehicles that are allowed to be sold. They plan for by 2020 it to be in Beijing 100% of the vehicles they're allowing. And the reason they're doing that is they find it's really difficult to enforce any kind of emission controls on individual vehicles because people bribe everyone at the inspection stations and they bypass their catalytic converters and whatnot. And it's much easier to control the emissions from a centralized facility. So you can really clean up your air through electrification. You can see that here. But if you electrify using low carbon electricity, and here it's about half, instead of 70%, it's about half coal, and here it's 35% coal, you get a dramatic reduction in national total CO2 emissions. This is the moderate one, and this is the ambitious one. And so if China moves forward with its electrification plans and its renewable energy plans, I think it's very likely that it's going to peak its CO2 emissions and start coming down before 2030. I think that they're really moving forward aggressively now.
Any idea, like the filters and masks are not sort of probably in the projections, but if you sort of full-scale supplied those things, right? How far, what would that do to mortality in China, right? When you started off with that picture, and I'm sort of interested, are they in the same ballpark? Obviously they're inconvenient and there's lots of things you don't like about them.
So most people, they're really miserable to use. Most people don't use them. Even in absolutely terrible pollution, they don't use them. The taxi that took me to the airport, I had a spare mask. I didn't need it. I said, do you want my mask? He says, no. No, thank you.
Right.
But the people who understand the importance of them, I had a spare mask in the university. I was like, anyone want it? And like immediately someone grabs it.
Yeah, but OSHA will tell you that those masks are incredibly inefficient. They do almost nothing. They're more for your mental state.
Is that true?
They don't
Well,
work.
that's what I'm asking.
The studies show they don't
You go
work.
And
to
there's-
any chemistry lab.
That's interesting. Okay.
And you wear one of those, you will be thrown out because they will not do anything for particles, silicate,
Really?
any of that.
The 3M masks are certified for something.
But the problem is that there are no seals, and
Oh,
they
yeah,
go right
okay.
around the
But
outside.
the HIPAA filters inside.
No,
right?
No,
they're
but
certified
no.
for dust.
They're-
They're certified for dust,
They-
but dust is not PM2.5.
Yeah.
And so
Oh,
the thing
okay.
is, they go around
Well, they're
the
also
side.
they're miserable to wear, and then there's also this positive feedback where a lot of people who can afford them are now putting particle filters in their offices, in their apartments. It takes a lot of energy to run those things.
Yes.
So really bad news as a long-term solution.
Yeah, no, I would think so. I just wondered where it was at.
So, okay, so in conclusion, there's opportunities for air quality and climate co-benefits. Reduction in solid fuel use in the residential sector is extremely important. Improvements in industrial energy efficiency are highly beneficial. But overall, electrification with decarbonized electricity provides the greatest opportunity to simultaneously improve air quality, reduce associated premature mortalities, and reduce CO2 emissions, according to our work. And so here you can see the same picture of Tiananmen Square in Beijing on a bad pollution day and a blue sky day. So there's real motivation to do something. And thanks to my collaborators and group members and funding sources.
Any final questions? We have a minute or two? Yeah. Yeah.
Yeah?
That was great. Really
Oh, thank
appreciate
you.
it. Really important. I mean, like, as important as it gets, so congratulations. So it looks like it's like 3-to-1 that the amount of benefits you get for climate as opposed to reduced mortality. That is 30% in your like ultimate super optimistic scenario versus only about 10 or 12%. No, not even, yeah, okay, 12% reduction in mortality. That doesn't seem that high. To just reduce from 100 to 88 or something.
So
So we get to my question, I guess, is what about morbidity? That is,
Yeah.
asthma and emergency room and like miserable life and missed days of work and all that kind of stuff.
yeah. So first thing I want to say is that these results are all contingent on what the scenarios are, right? So these are the scenarios that we developed. If they did something different, you would have a different result. You could get something higher or lower on this premature mortality scale. Yeah, I think morbidity is really important. Economists usually say, well, mortality has the highest value. And so we focus on mortality. Some work we did a while ago looks at morbidity as well. I think morbidity is really motivating, frankly, because it's miserable to be in terrible air pollution, getting sick all the time from it. But yeah, we haven't quantified that yet.
Do you have any idea what the policymakers think about morbidity or mortality or?
Like I said,
What do they
they
care?
declared a war on air pollution. They really are motivated to clean up their air. And the reasons and quantitative, relative to values, I'm not sure. Yeah?
Yeah, I mean, to follow up on Timon's point, this is in some ways a little bit depressing because these are big investments and you're seeing a 10% to 12% reduction in mortality in sort of the best case scenario. And I would just wonder, if, so mortality, you're right, it's not the only outcome, but one way to sort of put this in perspective is to say there's still a lot of smoking in China. Well, how does this compare to, say, a 20% reduction in smoking? And, I suspect that as an intervention doesn't offset CO2 emissions.
Well, let me just say about smoking that the first time I went to China was in 1990, and I was nearly smoked out of the room. I mean, every conference you went to, the rooms were small, everyone was chain smoking. I go to China now, there's no smoking any place that I've been in a public space or any meeting I've been in, there's no smoking. So they're working on that as well.
But that again lets you quantify or have sort of a benchmark, like, are these effects important? I mean, you said 1.6 million people in China are dying every year of outdoor air pollution. So, that's a huge number. So 10% reduction is great, but there's still 90% to go. So how does this compare to sort of other interventions, or how are we going to get to the point where you're on the steeper part of the dose response curve so that it's actually...
Right, well, like I said, this is just, the benefits you can get from reasonably feasible electrification interventions in the next dozen years. So there's certainly more that needs to be done across the board on a lot of things.
We're actually past our time, so why don't we continue the conversation upstairs? There's a party upstairs on the first floor with lots of wine and goodies, so please join us, and let's thank the speaker again.